Rabi's Commentary, Rudin's Principles of Mathematical Analysis, Chapter 1, The Real Field, Theorems 1.19, 1.20, 1.21, 1.22. Theorem 1.19, The Real Field. We now state the existence theorem, which is the core of this presentation. The proof is in the appendix to Chapter 1. Theorem 1.19. There exists an ordered field R called the field of real numbers, which has the least upper bound property. Moreover, R contains Q, called the field of rational numbers, as a subfield. The second statement means that Q is a subset of R, and that the operations of addition and multiplication in R, when applied to members of Q, coincide with usual operations on rational numbers. Also, the positive rational numbers are positive elements of R. The members of R are called real numbers. If x equals 2 and y equals 9, what is the smallest positive integer n such that this? Since y over x equals 9 over 2 equals 4.5, then n equals 5. If x equals 2 and y equals 10, what is the smallest positive integer n such that this? Since y over x equals 10 over 2 equals 5, then n equals 6. If we choose any x element of R, y element of R, and x greater than 0, is there always a positive integer n such that this? For sake of argument, if we could use the ceiling function, it seems that this would work. But is the ceiling function well defined? In other words, given a real number z, does there exist the smallest integer that is larger than z? What if the integers have an upper bound? Can we show that the set of all integers have no upper bound? Or can we show that if the integers have an upper bound, then we'll get a contradiction? Theorem 1.20a. If x element of real numbers, y element of real numbers, and x greater than 0, then there is a positive integer n such that this. Theorem 1.20 is usually referred to as the Archimedean property of R. Proof. Let's begin a proof by contradiction. Assume that the conclusion of Theorem 1.20a is false. That is, for all positive integers n, we have this. Let A be the set of all nx where n is a positive integer. Note that the set A is non-empty since this, and is a subset of R since this. Also, by our assumption, we have this, and so y is an upper bound of A. Since A is subset of R, A is not empty and is bounded from above, it follows that A has the least upper bound, supremum, in R. Denote this. From relations, we get this. It follows that alpha minus x is not an upper bound of A, as alpha is the least upper bound of A. Hence, there is some element of A which is larger than alpha minus x. That is, for some positive integer m, we have this. But then, this. But this. And m plus 1x is element of A by definition of A. Thus, we found an element of A which is greater than alpha. This is a contradiction, since alpha was supposed to be the upper bound of A by definition of the supremum. Thus, our original assumption was false, and so Theorem 1.20a is true. Theorem 1.20b. If x in R, y in R, and x less than y, then there exists a p in Q such that this. Theorem 1.20b may be stated by saying that Q is dense in R. Between any two real numbers, there is a rational one. Proof. Let x in R, y in R be such that x is less than y. Then y minus x is in R, and this. Thus y minus x is in R, and y minus x is greater than 0. So Theorem 1.20a, applied to a pair y minus x 1, furnishes a positive integer n such that this. Apply Theorem 1.20a again to pairs here to obtain positive integers m1 and m2 such that this. And this. Then this. Which combined with m1 bigger than nx yields this. Consider the set of integers b. The set B is non-empty, as minus m2 is in B. Additionally, the set B is bounded from above. Hence, by the least upper bound property of R, there exists a supremum alpha equals supremum B. Then alpha minus 1 is not an upper bound of B, and so there exists L in B, L greater than alpha minus 1. From inequality L plus 1 greater than alpha, it follows that L plus 1 is not in B. Then, for any k in B, we have k less than L plus 1 and k less than or equal to L. So L is an upper bound of B, L greater than or equal to alpha. On the other hand, L in B and L less than or equal to alpha. Consequently, L equals alpha, and we've just proved that any set of integers that is bounded from above has the maximal element. Denote M equals L plus 1, where L is the maximal element of B. Then this. From here, it follows that nx less than m and this, also this, now if we combine inequalities here, we obtain this. Since n greater than 0, we can divide the inequality by n, while the direction of inequality is preserved. Hence, it follows that x less than m over n less than y. Since m and n are integers, n greater than 0, we have that p equals m over n is a rational number. Thus, we've showed that there exists a p in Q such that x less than p less than y. This proves Theorem 1.20b. If x equals 64 and n equals 2, then is there a y greater than 0 such that y squared equals 64? Since this, then y equals 8. If x equals 64 and n equals 3, then is there a y greater than 0 such that y cubed equals 64? Since this, then y equals 4. If we choose any real x greater than 0 and any integer n greater than 0, is there one and only one positive real y such that y to the power n equals x? An affirmative answer is given by the theorem 1.21. Theorem 1.21. For every real x greater than 0 and every integer n greater than 0, there is one and only one positive real y such that y to the power n equals x. This number y is written nth root of x or x to the power of 1/nth. This will prove the existence of nth roots of positive reals. Proof outline. 1. Proving uniqueness. 2. Defining a set with the intended supremum. 3. Proving that the supremum is what we intended. 3.1. Assumption 1. Y to the power n less than x. 3.2. Assumption 2. Y to the power n greater than x. 3.3. Y to the power n equals x. 1. Proving uniqueness. In order to prove uniqueness, we will show that this implies this. For the sake of completeness, we will prove this using mathematical induction. Assume that this, and let Pn be the statement this. Since y1 less than y2, we have that P1 is true. Now assume that Pn is true for some positive integer n, that is, this holds. Since y1 greater than 0 and this, we have this. That is, this. Also this combined with this implies this. that is, this. Therefore, this. This shows that p n plus 1 is also true. By mathematical induction principle, Pn is true for all positive integers n. That is, y1 to the power n less than y2 to the power n. Thus, there cannot be two positive reals, y1 not equal to y2, such that this. Indeed, from what we just showed, contraposition implies this. 2. Defining a set with the intended supremum. Let E be the set consisting of all positive real numbers t such that t to the power n less than x. We need to show that E is non-empty, which we'll do with a direct proof. Let us first notice that if t less than 1, then t to the power n less than or equal to t for all integers n greater than 0. We can prove this using mathematical induction. For n equals 1, note that t less than or equal to t holds. Now, assume that this for some n greater than 0. Then this. Thus, t to the power n less than or equal to t for any integer n greater than 0. Therefore, it is of interest to find t such that this. Indeed, from what we just showed, it follows that this and t would be an element of E. The simplest such t is this. Since x greater than 0, we have that 1 plus x greater than 0 as well, and so this. Also, dividing the inequality x less than 1 plus x by 1 plus x implies that this. Thus, 0 is less than t less than 1. And since this, we have t less than x. Therefore, this and this implies that t to the power n less than or equal to t less than x. Thus, t equaling this is in E, and E is non-empty. Next, we need to show that E is bounded above. Let us first notice that if this, then this for all integers n greater than 0. We can prove this using mathematical induction. For n equals 1, note that s is greater than or equal to s. Now assume that this for some n greater than 0. Then this. Thus, s to the power n greater than or equal to s for any integer n greater than 0. Therefore, it is of interest to find s such that s greater than or equal to 1 and s greater than x. In that case, we would have that if t greater than s, then t is not an E, since this. In other words, S would be an upper bound of E by the law of contraposition. One such S is S equals 1 plus x. Indeed, note that S greater than 1 and S greater than x. Thus 1 plus x is an upper bound of E. Hence, we've showed that E is a non-empty subset of R which is bounded from above. Theorem 1.19 implies the existence of y equals supremum E, and we intend to show that y equals nth root of x. 3. Proving that the supremum is what we intended. We will use a proof by contradiction to prove that y to the power n equals x. We will show that both the assumption 1, y to the power n less than x, and the assumption 2, y to the power n greater than x, lead to contradictions. And so the only possibility which would remain is y to the power n equals x. This proof will require some factoring, and so let's include the following lemma. Lemma 1. For any a, b, and r, this. Note that this by the strong induction principle will prove this. First, we prove the base cases. Then, we'll assume the induction hypothesis this holds for all this. And now we have to show that this. So let's do the inductive step this. And thus we've proved that this. Corollary 1. If this, then this. If n equals 1, then the needed inequality turns to equality. Let n be bigger than or equal to 2. Since 0 less than a less than b, this. If we multiply both sides by b minus a greater than 0, then this. Using lemma 1, we get this. We could also prove the previous lemma 1 in the following way. 3.1. Assumption 1. Y to the power n less than x. Before we begin, if we think of y to the power n as a function of y, then small inputs of y should give small outputs of y to the power n. In other words, we can make y to the power n outputs as close to each other as we want, as long as y inputs are close enough to each other. This means that we have to consider this with a sufficiently small 0 less than h less than 1. Once we do this, then we would show this. And this would be a contradiction with the fact that y equals supremum e. Now, we need to figure out what is close enough and sufficiently small. Using the inequality from corollary 1, we have this. Also note that this. And so what we need is a 0 less than h less than 1 such that this. From here, note that if h less than 1, then we can replace the second h in our inequality, this. The expression on the right is greater than 0, and so we can choose an h that satisfies the inequality. Finally, we can start with our first assumption. 3.1 Assumption 1. Assume y to the power n less than x, and so this. Choose h so that 0 less than h less than 1 and this. We can choose such h since this. Note that this, as well as this. The direction of inequality is preserved since this, and so this. With the following inequality, this, if we let a equals y and b equals y plus h, then this. Thus, this and that. This contradicts the fact that y is an upper bound of e. 3.2 Assumption 2. Y to the power n greater than x. This section is analogous to Assumption 1. Before we begin, if we think of y to the power n as a function of y, then small inputs of y should give small outputs of y to the power n. In other words, we can make y to the power n outputs as close to each other as we want, as long as y inputs are close enough. This means that we have to consider this with a sufficiently small k greater than 0. Once we do this, then we should show that y minus k is an upper bound of e. The fact that y equals supremum e then would imply this, which is a contradiction. Now, we need to figure out what is close enough and sufficiently small. Using the inequality from Corollary 1, we have this. Also note that this. And so, what we need is a 0 less than k such that this. From here, note that if 0 less than k, then we can get this inequality. In the proof, we'll actually use the equality this. From this, we'll show that this. This is equivalent to proving the contrapositive, this. In that case, y minus k would be an upper bound of e. This would contradict the fact that y equals supremum e is the least upper bound of e. Finally, we can start with our second assumption. 3.2 Assumption 2. Assume y to the power n greater than x, and so this. Denote k equals this. Since n greater than or equal to 1, we have this. Note the inequalities, this. Overall, 0 less than k less than y. If t greater than or equal to y minus k, we conclude that this. Based on the corollary 1, this. Thus, this. Therefore, t not in E. Hence, by contraposition law, if t in E, then t less than y minus k. It follows that y minus k is an upper bound of E. But y minus k is less than y, which contradicts the fact that y is the least upper bound of E. 3.3. Y to the power n equals x. Since both assumptions y to the power n less than x and y to the power n greater than x lead to contradictions, using the law of trichotomy, we must have y to the power n equals x. Corollary 2. If a and b are positive real numbers and n is a positive integer, then this. Proof. Put alpha equals a to the power of 1/n and beta equals b to the power of 1/n. Then this, and so this, since multiplication is commutative. The uniqueness assertion of Theorem 1.21 shows, therefore, that this. Decimals. Let x greater than 0 be real. Let n naught be the largest integer such that n naught less than or equal to x. Note that the existence of n naught follows from the Archimedean property and the least upper bound property of R. Recall the proof of the theorem 1.20b. Having chosen this, let nk be the largest integer in this such that this. Let E be the set of these numbers, this. Then x equals supremum E. The decimal expansion of x is this. Conversely, for any infinite decimal, equation 2, the set E of numbers, equation 1, is bounded above, and equation 2 is the decimal expansion of supremum E.